everyone, so today Ihan and I will be presenting on chromatography. Specifically, we'll be presenting on high performance liquid chromatography, or HPLC for short, gas chromatography, and column chromatography. First, let's start with a very brief, let's just have a quick segue into paper chromatography, which we're probably all very familiar with. Paper chromatography is obviously the separation of different components of a mixture based on their differing solubilities in the same solvent, and the purpose of paper chromatography is to identify the different components of a mixture using their RF values. But the main concept in paper chromatography is the existence of the stationary and the mobile phase. And the stationary phase basically remains fixed in place and is usually a solid. And in paper chromatography, the stationary phase is paper. And then the mobile phase, which moves and carries the components of the mixture with it. In the case of paper chromatography, the mobile phase is the solvent. Yes. All forms of chromatography essentially rely on interactions between the mixture components with the mobile and stationary phases to separate the different components. Components that interact more significantly with the mobile phase will move faster and be eluted first, while those that interact more significantly with the stationary phase will lag behind and come out later. In the case of paper chromatography, components that are more soluble in the solvent interact better with the solvent particles, which is basically the mobile phase, and hence these components will travel faster and be closer to the solvent front. So let's move on to high performance liquid chromatography, which I'll be referring to as HPLC from now on. Some quick facts about HPLC. It's known as high performance liquid chromatography because the procedure is usually carried out at very high pressures of up to 400 atmospheres. It's also quite a fast process, and there are two main types of HPLC: normal phase and reverse phase, but we'll get to that later. And also, unlike paper chromatography, for HPLC you can actually collect the different mixture components if you want to.
Here is the setup for HPLC. Sorry for the very low quality picture. Yes. So first, as you can see on the left side, there's a reservoir that holds a solvent, which is the mobile phase for HPLC. There's a high pressure pump that is used to generate and control the flow rate of the mobile phase. An injector is able to introduce the sample into the continuously flowing mobile phase stream that carries the sample into the HPLC column. The column is usually filled with tiny silica particles, and these silica particles constitute the stationary phase. A detector is needed to see the separated compound bands as they elute from the HPLC columns. Because most organic compounds tend to be colorless, in order to be able to tell that there are a few different compounds eluting at certain points, you need to be able to have a suitable detector. The mobile phase that exits the detector can be thrown away or it can also be collected. And when the mobile phase contains a separated compound band, HPLC provides the ability to collect this fraction of the eluate containing that purified compound for further studies, such as mass spectrometry or whatever. Yes. So as the separated dye bands leave the column, they pass immediately into a detector. An appropriate detector has the ability to sense the presence of a compound and send its corresponding electrical signal to a computer data station where essentially the data will be processed to create a chromatogram. In order to choose what type of detector to use, it will really depend on the characteristics and the concentrations of the different compounds that are inside the mixture that need to be separated and analyzed. A common detector used is a UV detector, since many organic compounds absorb UV light of various wavelengths, and the amount of light absorbed will also depend on the amount of a particular compound that is passing through the beam at that time. This is a chromatogram, which represents basically a data generated by the detector that can help you to determine the proportion of different components of a mixture using the integrals. Sounds familiar, yes. So a series of peaks will rise from the baseline, which is drawn on the time axis, and each peak represents the detector response for a different compound. Next, let's move on to a concept known as retention time, which is quite similar to the concept of RF that are used in paper chromatography, except the retention time is what is used in liquid and gas chromatography. As the name suggests, retention time is essentially the time taken for a particular compound to travel through the HPLC column to the detector, basically how long it remains in the chromatography system. This time is measured from the time at which a sample is injected to the point at which the display on whatever detector computer shows the maximum peak height for that compound. Different compounds have different retention times, and for a particular compound, the retention time will vary depending on the pressure used, because that affects the flow rate of the solvent, the nature of the stationary phase, and the exact composition of the solvent, because this affects the interactions between the components of the mixture and the two different phases. and the temperature of the column also affects the retention time. If you want to use retention time as a way of specifically identifying the compounds, such as how you do that in table chromatography, you have to very carefully control these 4 different factors. So typically N-off for HPLC are introduced 2 of the variants that are usually used, and these 2 variants basically depend on the relative polarity of the solvent and the stationary phase. In order for the different compounds in the mixture to interact differently with the 2 phases, obviously the mobile and stationary phases should be of opposite polarities. In normal phase HPLC, the HPLC column is usually filled with tiny silica particles. Basically, the stationary phase is polar, and then the solvent is usually some kind of non-polar solvent like hexane. And the polar compounds in the mixture will stick longer to the polar silica, and hence the non-polar compounds will be the ones that pass through the column quickly and have a shorter retention time. For reverse phase HPLC, the column used is the same, but the silica is modified to make it non-polar by attaching long hydrocarbon chains to its surface. And to reverse the polarities, the solvent used instead is polar, for example, methanol. So in this case, it is now the polar molecules that will travel through the column more quickly as they interact with the methanol solvent. Reverse phase HPLC is actually a more commonly used form of HPLC. So moving on, Yihan will talk about gas chromatography.
Yeah, so moving on to GC, the story becomes quite different. Okay, GC here does not refer to your graphic calculator, but gas chromatography. So in gas chromatography, the mobile phase we use is not liquid, but gas. Helium gas is usually used, but nitrogen and hydrogen are also possible choices. One important thing to note about the mobile phase is that it must be oxygen-free, as you don't want your organic sample to react with oxygen. The stationary phase is usually more variable. It can be either a liquid or a solid. However, if a solid stationary phase is used, the chromatogram obtained will have less defined peaks. So the more commonly used stationary phase is still liquid. Gas chromatography works more or less in a similar way to liquid chromatography. The sample is first vaporized into gaseous state. The vaporized sample are then carried by an inert gas, your mobile phase, through a column containing liquid inside, the stationary phase. Substances that interact better with the mobile phase move faster in the column and will come out first, while substances that interact better with the stationary phase move slower and come out later. Now let's look at the instrumentation for GC. This is the structure of a typical gas chromatography machine. It consists of 3 main parts: the sample injection port, the column, and the detector. When the sample is injected, it is first vaporized and mixed with high-pressure carrier gas. Then the gaseous mixture is pressed through a liquid column. So there are 2 types of commonly used columns: the wall-coated open tubular, WCOT, and the support-coated open tubular, SCOT. WCOT, as its name states, has a thin layer of stationary phase, as indicated by the blue color here, coated on its column wall. On the other hand, the SCOT column wall is first coated with a thin layer of absorbent solid. The solid is then treated with the stationary phase. While SCOT columns are capable for holding a greater volume of stationary phase than the WCOT column due to its greater sample capacity, WCOT columns still have a greater column efficiency. There are many types of detectors available for GC. However, most of them have their limitations. Flame ionization detector can only analyze flammable samples. Thermal conductivity detector requires a high sample concentration. Electron temperature detector can only be used for halogenated hydrocarbons, while atomic emission detector is element selective. So, is there a one-size-fits-all detector? Of course. Think about what we have learned in structural elucidation. Something in gaseous state, high temperature, inject in a flow. Yes, this is our best friend, mass spec. The GC-MS system is widely used in analytical chemistry. However, the most commonly used method is still flame ionization detector, which use a hydrogen air flame to decompose the sample to emit ions and electrons for analysis. This is partially because most samples analyzed are organic and thus flammable. Another very important consideration is budgetary constraints. According to what I have found online, it takes about $500 to run a mass spec sample. Yeah, per sample, take note. Oops, unscrupulous monopolies, right? Compared to the price inelastic mass spec, flame ionization detectors seem to be a cute and sweet substitute, and is more widely used in research institutions. Talking about the retention time, unlike HPLC, which looks more into the polarity of the compound, in GC, we look more into the totality of the compound, in other words, its boiling point, temperature inside the oven, as well as the solubility of the compound in the liquid. This is quite easy to understand. The less volatile the compound is, the harder it is to keep in the gaseous state, longer retention time. The lower the oven temperature, the slower the mobile phase move, longer retention time. The more soluble the compound is in the liquid, the better it can be retained, longer retention time. Hotchong SRC is well known for having a lot of expensive instruments, like the IR spectrometer and UV-based spectrometer. If I don't remember wrongly, there's also an HPLC machine on level 2 chem lab, but it doesn't have a GC machine. Since GC is such a powerful tool for analysis, why the school doesn't want to invest one? Well, let's look at the pros and cons for GC. Okay, so for GC, as the mobile phase is a gas, it's easily separable from the sample compared to others using liquid as mobile phase. It can be connected to many detectors. Thus, it's especially suitable for identifying unknown mixture. Moreover, the column is reusable. One column is capable for about 1,000 plus analysis, so it's very environmentally friendly. However, there are quite a few terrible disadvantages that stop the school's itchy finger from investing a GC machine. Okay, first and foremost is the safety consideration. And imagine, if some careless student happened to introduce some oxygen gas as impurity into the gaseous mixture, which is under a high temperature and high pressure. Okay, congratulations. You are able to achieve all the chem students' dream, blowing up the school lab. Secondly, it's still about the universal concern, the budget. GC involves the use of high-pressure helium gas, which is super expensive and hard to store. The column is also kind of expensive, although it can be reused. Last but not least, frequent calibration is required. Those who have done research must know how annoying it is to do calibration. It is very troublesome to calibrate a GC. Just like spectroscopy, you always need a straight horizontal baseline before injecting any samples. But sometimes baseline can even give you a sine graph. Okay, moving on, here comes my favorite. Presenting to you the most widely used separation technique, thousands of researchers' nightmare, column chromatography. The basic principle of column chromatography is pretty much the same as HPLC, which involves a liquid mobile phase flowing through a solid stationary phase. Then you get your compound separated and collected in different fractions. The key difference between column chromatography and HPLC, as well as GC we talked about just now, is that it is more used as a separation technique rather than for analytical use. GC and HPLC are more used as analytical tools due to their high sensitivity. However, they usually have very limited capacity. The samples are injected in micrometer cubes, and if you run too much sample at one time, you may spoil the super expensive column. Unlike the intricate GC or HPLC, column chromatography is something much more violent yet simpler. Okay, as you can see here, right? This is a column chromatography setup. As you can see, compared to the teeny tiny column with diameter less than 1 cm using HPLC and GC, columns of column chromatography can have a diameter larger than 10 cm. You can literally dump all your samples inside and wait for it to separate. What's more, the stationary phase is disposable. This prevents cross-contamination of the samples. Most importantly, what do we consider most when we are doing mass production? Yes, the cost. Column chromatography is super cheap, as the stationary phase is just your normal silica gel. As column chromatography is so convenient, why would I still say it is the nightmare of thousands of researchers? Okay, let's watch a video.
As a method for carrying out column chromatography, you may be given slightly different instructions when you do this in the lab, but the principles will be the same. First of all, a small piece of cotton wool is placed in the bottom of the column to prevent solid material from going into the tap. Different columns may have different types of tap, but obviously the idea will be the same. Next, a small amount of sand is poured in to a depth of about 1 centimetre. Here you can see the sand forming a level surface on top of the cotton wool. We then take the appropriate amount of silica in a beaker, and this is then made into a slurry using the solvent we're going to run the column with. This solvent is known as the eluent. Here you can see us swirling the silica with the solvent before pouring it into the column very carefully. Again, a funnel should be placed in the neck of the column to assist with pouring. And you will need to occasionally swirl the beaker to ensure that the silica doesn't settle out in the bottom of the beaker. Where appropriate, more eluent should be added to reform the slurry to assist with pouring. You may need to do this several times. Should the level of the eluent get close to the top of the column, then some of it should be removed by opening the tap. We can run this into the beaker, which will then assist us in making a slurry with the remaining silica. And finally, we've transferred all of our silica into the column. Now we need to run some of the eluent out of the column so that it comes down to the level of the silica. It's crucial that you don't allow the silica to run dry, so you need to keep a close eye on the level of the eluent and close the tap at the appropriate moment. Here you can see we've run the eluent down to the correct level so that the top of the silica has not dried out. The next stage is to load our crude compound onto the column. First of all, we need to dissolve it in a small amount of the eluent. It's important to ensure that all of the crude compound has been dissolved. And then the resulting solution can be added to the column using a glass pipette. Here you can see the solution is being added evenly around the sides of the column. Now we add some sand to a depth of about 1 centimetre on the top of the column. This will protect the silica as we add eluent. And here you can see us topping up the column with eluent. And we're now ready to run our column. So we open the tap at the bottom of the column, and this allows us to collect our first fraction. In this case we're collecting the fractions in test tubes, but depending on the size of your column you may use sample vials or even conical flasks. Once collection is complete, we can close the tap momentarily to move on to collect fraction number 2. And this process can be repeated any number of times to collect as many fractions as are required. Because our compound is coloured in this case, we can actually see it moving down the silica. This will give us a good indication as to when it's actually eluting from the column. In cases where you can't see the compound because of any colour, you can use TLC to analyse the fractions to identify the presence of different compounds. And as the level of the eluent approaches the sand, it's important to make sure that you top it up. We can then continue to collect fractions, and in this case you can see that the yellow band in the silica is approaching the bottom of the column. If we look closely at this particular fraction, we can see that the solvent has a yellow colour, telling us that our compound is eluting. Of course, in other cases, as mentioned previously, you'd have to use TLC to identify the presence of a compound. And here we have a full set of fractions. We can now collect any compounds that are present by removing solvent, and this would most commonly be done using a rotary evaporator.
Okay, as you can see in the video, it is super troublesome to set up the column. Also, you have to wait for very long for all fractions to come out. These are still minor issues. The most fantastic part for column chromatography is that you have to identify different fractions. If the compound is colored, it's still okay. But as we know, most organic compounds are colorless. Oops, so what can we do? As you can see in the video, the only solution is to collect as many fractions as possible into different test tubes. This means you have to keep rotating different test tubes and take note not to mess up the order. If your research project happens to have a tight timeline, which is the case of most of the time, you have to run a few column chromatographies at the same time. One column is a mess already. Okay, several columns, terrible. Then here comes another problem. How do you know when does the compound start to come out and when does it fully come out? Well, you have to run a test for content in all test tubes. Okay, in reality, you don't need to run the test for every single test tube, but it depends a little bit on luck as well. If you are lucky enough, you are able to identify the starting point and the end point quite fast. But if you are a little bit unlucky, too bad. Okay, to sum up, today we have gone through the principle of chromatography and different types of chromatography, including paper chromatography, high-performance liquid chromatography, gas chromatography, and column chromatography, and their applications in labs. Hope you have enjoyed our presentation, and thanks for listening. Also, we have prepared interesting tutorial question for you. Yes, have fun doing it. Thanks.
Yeah, I'll pass the time now to a group that's doing steady state approximation for kinetics. Okay, so let's welcome the speaker. Okay. Good afternoon, everyone. So our group today will be presenting about the steady state approximation in reaction kinetics. So our group is composed of Lin Xuan, Xiaobing, which is myself, Lauren, and Jiayang. So just a recap of some stuff about reaction kinetics from our H2. So basically, reaction kinetics is a branch of physical chemistry, which is concerned with understanding the rates of chemical reactions. So basically, we just want to know how fast things are being made or being used up. Okay, so what is a reaction mechanism? So a reaction, usually they are not completed in just one step, so it's a sequence of steps. And a reaction mechanism is a sequence of elementary steps that add up to the overall reaction. The rate determining step is the slowest elementary step of them all. And the rate of this rate determining step determines the overall rate of reaction. And all steps before this step, the rate determining step, will affect the overall rate. The rate law can be calculated as the rate of formation of the product. So, what is steady state? In chemistry, usually we define the steady state as a situation in which the variables remain constant despite processes that strive to change them. So one good way to think about this would be all the stuff that we see in our math questions, where we have someone trying to pour stuff into a bathtub, but at the same time, they are pouring it out. And so this steady state is achieved when the rate of stuff being added in is the same as the rate of stuff being poured out. So the amount of water in the bathtub doesn't change, even though both taps are trying to do different things, adding water in and taking water out. So we need to draw a distinction between the steady state and a dynamic equilibrium. So in the steady state, the formation and the removal process is not simply a reverse of one another. So the reactions, the reactants, and the products are changing. On the other hand, in the dynamic equilibrium, we see that the reactants and products have reached a stage in which they're both constant. So how can we really apply this steady state approximation in reaction kinetics? So we can observe this general reaction of A to B to C with the rate constants as K1 and K2 as shown. So from this series of steps, we can derive the rate of change of concentrations for each A, B, and C. So for example, the rate of change of concentration of A will simply be how fast it is being used up. So that will be the negative because it's being consumed of the rate equation of the first step. So K1 times A. For example, for intermediates such as B, since it is being involved in two steps, firstly in the production in the first step, which is represented by K1A, as well as being consumed in the second step, which is represented by K2B, we have to combine both of them and express the rate of change of B as such. And we can simply do the same thing for C. So it's important to note that for the initial conditions that we shall set for this reaction, we shall start with amount of A as A naught, and B and C, we assume that there is none of them at the start. And since each step is a one-to-one conversion of reactant to product, the sum of all the concentrations will equal to A naught by conservation of mass. So now we need to do a bunch of math. Yeah, so from the first step, right, we have a seemingly simple equation of dA over dt. So what we can do is to manipulate it to bring the same variables over to one side. So all the variables with the concentration term over to the left and the others on the right. Here we can do an integration. So now we will try and integrate it from time equals to 0 to a certain time t. So as you can see on the left-hand side, we will use the corresponding concentrations of A. So at the start, it is A naught when time equals to 0. And at time equals to t, we just let it be represented by A. So by integrating it, we get this equation, which can be manipulated to express A as a function of time. Now, we can substitute in the value of the concentration of A into the rate of change of B and do another integration. So with this concentration of B, we do it one more time and integrate it again, and we have a very, very complicated equation here. And as you can see, this is quite undesirable as it's very pain. Yes. So now I'll pass the time on to Lin Xuan to tell you more of how we can use steady state to make our lives easier.
So as Xiaobing has introduced before, with the steady state approximation, we assume the concentration of the reaction intermediate to be a constant, so that the rate of formation of the reaction intermediate is equal to the rate of removal of the reaction intermediate, so that the overall rate of change of the concentration of the reaction intermediate is equal to 0. Yeah. Basically, we will be applying this approximation for the middle of the reaction where the concentration of the reaction intermediate has stabilized. So with the steady state approximations, because we have identified B as the reaction intermediate, the rate of formation of the B is simply given by K1 times the concentration of A, while the rate of removal of B is given by the B, K2 times the concentration of B. So we can simply equate these two expressions and manipulate it to get the B equals to K1 over K2 times the concentration of A. Yeah, and then because the overall rate of reaction is given by the rate of formation of the final product, which is C, the rate of formation of C is given by K2 times the concentration of B. So we can substitute in the expression for the concentration of B and do an integration. So after that, we'll be getting the expression for the concentration of C as such. Yeah, so comparing the two results, we can see that the second equation is actually an approximate form of the first
equation, whereby the K2 is much greater than K1. So that the second term, that the minus K1 times 1 minus blah, 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 that thing is much smaller than the K2, that term. And the denominator will be simplified into K2. So that this, so basically equation 2 is just an approximate form of equation 1. And because we have the K2 is much greater than K1, this indicates that the concentration of the reaction intermediate actually remains very low during the reaction. Because as soon as one reaction intermediate is produced, it is consumed by the second reaction. And this further proves that the assumption that the rate of formation is can be approximately equal to the rate of removal. Yeah, and we need to take note that the steady-state approximation is only applicable for reaction intermediate, because as the reaction progresses, the concentration of reactants and the concentration of products will be constantly changing. And the steady-state approximation is not applicable for the start of reaction or the end of reaction, because at the start, the concentration of the reaction intermediate hasn't stabilized yet. So we can't simply assume that the rate of formation is equal to the rate of removal. And lastly, the concentration of the reaction intermediate has to be low, because if the reaction intermediate concentration can reach a very high level, that means the rate of formation of the reaction intermediate is much higher than rate of removal, which violates our approximation. Yeah, so now I will pass the time on to Jia Yang, who will explain the first example of PDA. Yeah.
All right, so I'll be explaining this example on the formation of NO2. So this will, I guess, help to serve as something to concretize these ideas into like how you can actually apply these in solving these kinds of problems. So the first one is the formation of NO2. We'll be going through another example later. And this reaction is two NO molecules react with one oxygen molecule to form two NO2. Right. So some of the general steps that we'll be following in this like solving process for steady-state approximation problems will be as follows. Firstly, we identify the reaction intermediates, which are from the elementary steps. And then step 2 is find all the elementary steps that involve this intermediate. And then we write out the rate of formation and the rate of removal of these reaction intermediates and equate them. And then lastly, we have fun with algebra manipulation. Yeah, so for this specific reaction, we have two elementary steps. Firstly, two NO molecules are in equilibrium, like react in equilibrium to form N2O2. So the forward reaction rate constant is K1, and the backwards rate constant is K minus 1. And then in the second elementary step, N2O2 reacts with O2 to form two NO2 molecules. So the intermediate in this case would be N2O2 because it is formed during the reaction in the elementary steps and consumed in the elementary steps as well. So now we can start solving for the rate equation. And by using steady-state approximation, we know that the rate of formation is equals to the rate of consumption. So in this case, the rate of formation is given by the forward reaction for the first elementary step. So that means K1, the forward rate constant multiplied by the concentration of NO squared, because there are two NO molecules involved here. Now for the rate of consumption, we can look at the reverse reaction for the first elementary step, which is N2O2 forming two NO molecules. So that is the reverse rate constant multiplied by the concentration of N2O2. And then we need to add on the second elementary step, so K2, the second rate constant, and then multiply by the concentrations of N2O2 and O2. So now, because of the steady-state approximation, we know that the rate of change of the concentration of N2O2 is actually 0. So we have this this expression on top is equals to 0. So by rearranging this equation, we will get this this equation, and then the rate of reaction is given by these expressions. So the first one is by definition. The rate of reaction is given by how quickly NO2 is produced, and we add a half in front because for every 1 mole of the reaction mix, for for every 1 mole of oxygen, so of the reaction mixture, I guess, we get 2 moles of NO2. So we multiply this this change in NO2 concentration by half. And then for the second one, we get that K2 multiply K2 times N2O2 times O2, which is equals to how quickly NO2 is formed, is equals to this rate as well. And finally, by substituting in this concentration and N2O2 term, we will get the last equation, which is here. All right, so now we can consider 2 possible cases using this reaction. Firstly, when K2 is much greater than K minus 1, we can basically ignore this K minus 1 term, and then we can cancel off the O2 and the O2 concentration and the K2 term. And finally, we'll get this K1 times NO2 concentration squared equation. Right, and then the opposite case where K minus 1 is much greater than K2, for this, we can basically ignore this term because K2 is very small. So now we can get this equation. So this actually agrees with the experimental data. So now Lauren will be sharing about the SN1 reaction example.
Okay, so our next example will be about the SN1 reaction, which we will all be more familiar with since we've studied it before. Right, so in this case, we're going to be talking about the reaction between hydroxide ions and trimethylbromomethane, which occurs according to this equation that you see, chemical equation that you see here. So we can break this SN1 reaction down into 2 elementary steps, as shown here, and we can identify the carbocation intermediate form, which is indicated here. Okay, so by steady-state approximation, we can assume that the rate of change of concentration of the carbocation intermediate is 0. So this means that the rate of formation of this intermediate is equal to the rate of removal of the intermediate. So over here, we can see K1 times concentration of the bromoalkane, which you can see is over here. It's the rate equation for the forward reaction of the first step. And then meanwhile, we can get the rate of removal of this carbocation intermediate, which would simply be the rate equation for the reverse reaction of the first step, added to the rate equation for the second step. And when we rearrange, we can get this equation that you see here. All right, so now we can substitute the equation that we obtained in the previous slide into the rate of formation of trimethylmethanol. Right, so over here, when you do that, you will get this expression. Okay, so now since K2 is much larger than K minus 1, we can assume that K minus 1 will be negligible relative to K2. So you can simply ignore this term, and then you will get this approximation that you see here. And cancelling out the terms of K2 and concentration of OH minus, you will get this equation, which is actually consistent with our experimentally derived order of reaction. So now let's consider a few scenarios. So at the beginning of the reaction, our concentration of bromide is low and that of hydroxide is high. So let's again reference this equation that we got from steady-state approximation. Now, since as stated earlier, concentration of bromide is low and that of hydroxide is high, so we can treat K minus 1 times concentration of Br minus as being negligible relative to K2 times concentration of hydroxide ions. And hence, basically what we did is kind of similar to what we did earlier on in the previous slide, where we ignored this term of K minus 1 times concentration of bromide ions to get this expression over here. And again, cancelling, we will get rate is approximate to K1 times concentration of the bromoalkane. So hence we can make the conclusion that this reaction is first order with respect to the concentration of the bromoalkane and zero order with respect to the concentration of the hydroxide ion, which we have all learned before. Now let's consider another scenario. Now towards the end of the reaction, concentration of Br minus will be high and that of hydroxide ions will be low. So again, referencing this equation, we can now treat the concentration of hydroxide ions as negligible relative to that of bromide ions. which is kind of the opposite of what we did before, like in this previous slide. So now instead of ignoring this term, we can ignore the term K2 times concentration of hydroxide ions, and then we'll get this approximation here. Hence, we can make the conclusion that towards the end of the reaction, it will approach first order with respect to the concentration of hydroxide ions. Now let's consider one last scenario, okay? So for some reason, we're deciding to add Br minus in large excess to the reaction mixture. Okay, cool. So again, we consider this rate equation that we got. All right, so since Br minus is in large excess, we can make two conclusions. Okay, first of all, we can treat K2 times concentration of OH minus as being negligible relative to K minus 1 times concentration of Br minus. So then again, you kind of just ignore the K2 times concentration of hydroxide ions term, and then you get this approximation. Now the second conclusion that we can arrive at is that the concentration of bromide ions is relatively constant. So what we can do here is factorize this term out to form this fraction over here, and we can treat this fraction as being relatively constant. And then we get a new rate equation of sorts. So now we can see that the reaction is overall second order, since you get the overall order of reaction from the individual orders of reaction, which is just 1 plus 1. Quick math. All right, so now we've actually prepared a tutorial question, but I'm not sure there's enough time. Okay, yeah, it will be uploaded. Thank you.
Okay, thank you for the presentation. Okay, I don't want to scare you all, but if you have read the learning outcome of your organic mechanism in your history syllabus, steady state approximation is actually in your learning outcome. Okay, it was in a small section in your lecture notes. All right, but don't worry. Okay, you don't need to know much too detail about the math. Yeah.
Good afternoon, everyone. We are Gina, Yixing, Ruixuan, and Yiting. Today, we will be presenting on organolithium reagents. Oh, okay. So what are organolithium reagents? Organometallic reagents are organic reagents which contain carbon-metal covalent bonds that have large dipole moments. The metal atom will carry a significant partial positive charge, while the carbon atom will carry a large partial negative charge. This dipole moment is so large that the reagent behaves almost like an ionic salt. We will be focusing on organolithium and Grignard reagents. For this presentation, when we say organometallic compounds, we are referring specifically to these two compounds. Here's what we'll be covering today. So first, let us take a look at the structure of organolithium and Grignard reagents. Organolithium reagents contain an alkyl group bonded to a lithium atom, while Grignard reagents contain an alkyl group bonded to a metal halide. The halogen in Grignard reagents can only be chlorine, bromine, or iodine. In general, the metal or metal halide group bonded to the alkyl group should have an oxidation state number of +1. So for organolithium reagents, the lithium group has an oxidation state number of +1, whereas for Grignard reagents, the MgBr group combined has an oxidation state number of +1.
Okay, so now I'll be moving on to the reactivity of these reagents. Okay. Okay, so comparing organolithium and Grignard reagents, organolithium reagents are more reactive. So this is because lithium is more electropositive than magnesium, and hence the carbon-lithium bond has a greater charge separation compared to the carbon-magnesium bond. Next, we compare primary, secondary, and tertiary organometallic reagents. The metal atom or metal halide may be bonded to a primary, secondary, or tertiary carbon atom, as seen on the screen. These organometallic reagents will have different reactivities. The greater the number of bonded alkyl groups, the more reactive the reagent. So this is because the reagents can be thought of as ionic salts. They can be split into a carb anion and a metal or metal halide group. So of course, this is not the real mechanism which we'll be covering shortly. As seen from the previous slide, the inductively electron-donating effect of the alkyl groups will intensify the negative charge on the carb anion, making it more reactive. Hence, the more substituted the carbon atom, the more reactive the reagent. From this, we can also derive that aryl organometallic reagents are not very good Bronsted bases or nucleophiles when carrying out typical organometallic reactions, which require lone electrons on the carbon atoms bonded to the electropositive group. As the lone electrons on the carb anion will be delocalized into the benzene ring, they become activating groups, which make the benzene ring more reactive instead. Hence, reactions like nucleophilic substitution will preferentially occur. Vinyl organometallic reagents, which are bonded to a CC double bond, will have the metal or metal halide group bonded to sp2 hybridized carbon atoms. So these reagents are surprisingly unstable. To figure out why, we need to look at how these reagents are synthesized. And the synthesis of such reagents occurs via a mechanism called single electron transfer. This mechanism includes homolytic fission reactions, which involve radicals and radical ions. As such, the hybridization state of the sp2 hybridized carbon atom will change from sp2 to sp due to the presence of a lone electron in a p orbital. The CC double bond will now be between a sp2 carbon and an sp carbon, and this is unstable because the orbitals will have different sizes, preventing effective orbital overlap. And here's the mechanism for the synthesis of organolithium reagents. As can be seen, the halogenal alkane and lithium reagents are required as a 1:2 ratio. Ionic lithium bromide is also formed as a byproduct. And as you can see, this occurs via the single electron transfer mechanism. For Grignard reagents, the halogenal alkane and magnesium reagents are required in a 1:1 ratio, and there are no byproducts formed. Alkyl fluorides are not used as starting reagents for these reactions due to the strong carbon-fluorine bond, which is not easily broken. Hence, only Grignard reagents containing chlorine, bromine, and iodine can be formed. So, moreover, the synthesis of organometallic reagents usually takes place under anhydrous conditions in the absence of oxygen. This is as the synthesis process involves reactive metals, which may react violently with water or get oxidized to oxides, reducing product yield. Moreover, the organometallic reagents are strong bases which may react with water. Okay, so now I will be talking about a few reactions of organolithium and Grignard reagents. So to recap, organometallic reagents are very strong nucleophiles. As mentioned by Yiting, the carbon-metal bond is very polar due to large electronegativity difference between carbon and lithium or magnesium. So this gives the carbon atom a very large partial negative charge, making it very nucleophilic, which will be very useful in a lot of organic synthesis reactions. Due to the high charge density of the carbon, organometallic reagents can also act as very strong bases. So they cannot be added to other acidic reagents, even like mild acids like water or alcohol, because this will result in acid-base reactions occurring. Yeah. So in the following slides, I will share 3 of the reactions that organometallic reagents can undergo. So firstly, both organolithium and Grignard reagents enable carbonyls to undergo nucleophilic addition to form alcohols. The mechanism is similar to the one we learned in H2. So the nucleophile, which is the carbon attached to the lithium, in this case for organolithium reagents, will attack the partial positive carbonyl carbon, pushing the electron towards the oxygen here. Yeah, and the oxygen will then be protonated via addition of an acid to form an alcohol. The first step of the reaction is carried out in dry ether for Grignard reagent and in hexane for organolithium. So the second reaction is the nucleophilic substitution of epoxides to form alcohols. I'll use the Grignard reagent to explain this reaction. So the Grignard reagent is added to epoxide in dry ether and heated. The ring opening occurs via SN2 mechanism. So basically, the magnesium of the Grignard reagent will coordinate to the epoxide oxygen here to make it a better leaving group. So when the negative carbon here attacks this C, this will result in the electrons of this carbon being pushed to oxygen, opening the ring. Yeah, so in the case of substituted epoxides, the nucleophile will attack the less substituted carbon because it is less sterically hindered and more accessible by the nucleophile. So this will react faster. So if the carbon is chiral, there will be a stereochemical inversion. So the so after the electron pushing, this will result in the O having a negative charge, which so basically after that, the O will be protonated to form the alcohol. So the next, this reaction is specific to organolithium reagents. So this reaction is called carbolithiation, which is the addition of an organolithium reagent across a CC double bond to generate a new organolithium species. So just a disclaimer, we couldn't find a mechanism for this reaction online, so we proposed one with reference to this mechanism called anionic polymerization, which is what is proposed by online sources. Yeah, so because organolithium is a very strong nucleophile, it can attack the last carbon here, which will result in a series of electron pushing into the benzene ring. Yeah, so in the end, this carbon will have the negative charge. And this lone pair will then drive the attack of the positive lithium ion by the CC double bond. Yeah. So this whole process repeats to elongate the chain, as you can see over here. And you can terminate the reaction by addition of methanol, which will replace the lithium with a CH3 group. Yeah.
Okay, so next I'll be doing a summary of Grignard versus organolithium reagents. So the first difference between organolithium reagents and Grignard reagents is the formation. Organolithium reagents form by substituting the halogen, whereas Grignard reagents form by inserting itself between the carbon and halogen. Secondly, there's a difference between the strength of organolithium reagents and Grignard reagents. Organolithium reagents are a much stronger nucleophile than Grignard reagents. As such, organolithium reagents are more reactive than Grignard reagents. So what are some advantages of using organolithium reagents? Because it is a stronger nucleophile, it can undergo this reaction called lithium-halogen exchange, which we didn't really cover in our presentation, but you can see based on the diagram here. Additionally, organolithium reagents allows for nucleophilic addition between more sterically hindered organolithium and carbonyl. So as you can see in this diagram, adding organolithium reagent will give you a product, but Grignard reagent will not. Some limitations of organolithium reagents is that as organolithium is both a strong base and a strong nucleophile, it will inevitably form elimination product as a side product during substitution reactions, as illustrated over here. So elimination is always a competing reaction. Furthermore, steric hindrance is a major factor, so the alkyl halide must be primary or secondary, but not tertiary. Next, I'll be moving on to talk about the industrial applications of organolithium reagents. Organolithium reagents are used as an initiator for anionic polymerization, producing various elastomers. Basically, they are polymers with both viscosity and elasticity, as you can see in this diagram. They are used in the synthesis of tires, soles for shoes, and insulating elements. It can also be used in the asymmetric synthesis in the pharmaceutical industry. Now, I will be sharing more about the industrial applications of the Grignard reagent. Due to its ability to form carbon-carbon bonds, Grignard reactions are very essential in the synthesis of organometallic products. It is most widely used in the manufacture of pharmaceutical drugs. For example, Grignard reagents are used to synthesize ibuprofen, which is an anti-inflammatory drug that relieves pain and reduces swelling. To form ibuprofen, isobutylbenzene, which is product 1, first undergoes electrophilic substitution with an acyl linium ion to form 2. The ketone in 2 is reduced by any BH4 in methanol to form 3. The alcohol in 3 then undergoes SN1 with hydrochloric acid to form 4. And in step 4, the Grignard reagent is being formed by reacting magnesium in refluxing ether. Finally, a nucleophilic attack by Grignard's reagent onto CO2 forms 6, followed by acidification. So we have prepared some tutorial questions to try on your own time. But in the interest of time, I'll be only going through question 1 as an example. So for question 1, bromoethane first undergoes nucleophilic substitution to form ethanol, which then undergoes oxidation to form a carboxylic acid. In a separate reaction, magnesium and ether are added to bromoethane to form a Grignard reagent. The Grignard reagent and carboxylic acid then form a germinal diol. This reaction occurs as the Grignard reagent is a strong nucleophile, although the carbonyl carbon in carboxylic acid is less electron deficient. As the germinal diol is unstable, it loses water to form butanol. So the rest of the answers will be uploaded. Thank you.